Let's revisit the question of how do we convert proposition functions into propositions. One way we saw is if I had the proposition x plus 1 equal to 3, if I had a proposition function x plus 1 equal to 3, I can convert it into a proposition by assigning x a value. Another way we can do this is by using quantifiers, and we have two types of quantifiers, universal and existential. So let's look at what we mean by universal quantifier. The universal quantification of p of x, we write this as for all x p of x. This is a proposition. It is true if and only if every x in the universe of discourse that we are talking about has the property p. So if x came from 1 through 5 integers, then we want this property to be true when x is 1, x is 2, x is 3, x is 4, x is 5. If x comes from integers, then it is a property that is going to be true of every integer, and so on. So if every x in this universe of discourse satisfies the property p, we say for all x px is true, otherwise we say for all x px is not true. We call for all the universal quantifier, and we should read for all x px as, we should read this formula for all x px as for all x p of x. Or we can also say for every x p. Let's look at an example. Suppose we want to consider the proposition every student in this class has studied calculus. We are not interested in whether the statement is true or not. We are interested in writing it using proposition functions and writing it as a proposition. So we can say let p of x is a proposition function that denotes that x has studied calculus. So for all x px, where the universe of discourse is the students in this class, would capture the requirement that every student in this class, for all x is from a student from this class, p of x is true, that means x has studied calculus. There's another way we could do this, but using a different universe of discourse. Again, p of x denotes the same thing, x has studied calculus. Let's say we introduce another proposition function s of x that says x is in this class, and the universe of discourse is a set of all students. In this case, I could write it as for all x, s of x implies p of x. That means for every student, if they happen to be in this class, that is if they satisfy this, then they have studied calculus, that is p of x is true. So we can think of universe of discourse as a conjunction with a lot of things that we are conjuncting together. This works only if the universe of discourse that we have is finite. So in that case, for all x px means p of x1 and p of x2 and blah 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 and p of xn, where x1 through xn are values in the universe of discourse. Note that we can't do this if the universe of discourse is infinite, because there is a rule that says formula that we write has to be finite in nature. And that is part of the reason why we need universal quantifiers, because if we need to talk about cases where the universe of discourse is infinite, and we want to do that because we would like to talk about integers, real numbers, rationals, etc., in which case we need to have a way to write this formula that describes something about every integer in a compact fashion. Once again, note that for all x px is a proposition, In other words, it has a value of either true or false. Existential quantifier is the dual of universal quantifier. So existential quantifier of p of x, we write it as ex px. E is sort of backward, uh, which means one or more x in the universe has the property p. Note that existential quantifier just says there exists somebody who has the property p. There could be more than one having this property p. This operator that looks like a backward e is called existential quantifier, and it is read as there exists an x such that p of x, or there is at least one x such that p of x is true, or for some x p of x. Let's look at an example. Let's say px is a proposition function that says x is greater than 3. What is the truth value if the universe of discourse is the set of real numbers? Now the here the proposition that there exists p of x is true because I can definitely find a real number such that that real number is greater than 4. Sorry, the real number is greater than 3. One possible value for this is x is equal to 4. What if we change the universe of discourse to negative numbers? Well, in that case, there exists x p of x would be false because I cannot find a negative number that happens to be greater than 3. If the domain is finite, then existential quantifier is basically a long disjunction. So there exists x p of x is p of x1 or p of x2 or p of x3, keep going until p of xn. Note that this works only if the universe of discourse is finite. If it is not finite, then this doesn't work. Once again, there exists x p of x is a proposition. So here is a summary of the quantifiers. For all x px, it is true when px is true for every x in the universe of discourse. It is false when there is some x in the universe of discourse for which p of x is false. There exists p of x is true when you can find some x in the universe of discourse where p of x is true, and it is false if p of x is false for every x in the universe of discourse. Once again, we have reached the slide check before you go ahead. Here I have two proposition functions px and qy. Px is x greater than 3, qy is y less than 5. Your job is to determine whether the formula that I have given on this slide are evaluating to true or evaluating to false. Now the actual evaluation will depend on universe of discourse. So I have looked at three different universe of discourses. One is a set of integers that will be positive and negative. Another one is another universe of discourse is just the numbers 7, 8, 9, and the last one is the set of real numbers. I'm going to wait here, give a 30-second or so pause. I have a next slide that has the answers. I want you to check if the answers you get are what you expect, and if they are not, then I want you to check with me or TA to see where the misunderstanding may be. Please check the answers that you have. And if there is a question, please let me know, and we can discuss this in class.